Hello there, I'm Phone Yuan, presenting our CVPR work, KITRO, which refines human mesh by leveraging 2D clues and a kinematic-tree rotation approach. SOTA human mesh recovery, HMR, methods regress pose, shape, and camera parameters directly but often misalign reconstructed parts with 2D evidence. Like here, the legs should be one up and one down. Therefore, 2D keypoints are commonly used to refine 3D human meshes. Previous methods optimized the pose and shape parameters with a reprojection loss on 2D keypoints. Such an approach, while simple and intuitive, has limited effectiveness. Why? We observed two interesting phenomena. First, optimizing solely on 2D reprojection does not account for depth ambiguity, so is hard to find the optimal solution. Like here, although after simplify refinement it has a better 2D alignment, but sacrifices the depth accuracy. Therefore, can we explicitly model the joint depth? Second, refinement tends to favor end joints, like hand or foot, over joints closer to the root, like shoulder or collar, due to divergent gradient updates. Therefore, can we derive a closed-form solution and take the kinematic tree into account? Motivated by the above two drawbacks. In this work, we offer the key insight that joint depth can be solved explicitly in closed form. Given 2D keypoints, parent joint depth, and bone length, we can deduce two possible bone directions, one pointing toward the camera, the other pointing away. By accounting for depth, we can enhance depth accuracy and obtain an ideal 2D fit simultaneously. Having two possible depths for every joint naturally forms a binary decision tree along kinematic chains in the human body. Any path traversing the tree is a hypothesis, so our goal is to select the optimal path which generates the overall pose refinement. Such a strategy has a more global view of the human kinematic tree, so it can equally improve end joints and the joints near the root. Our framework iteratively refines camera, shape, and pose parameters. For camera refinement, the camera translation T** operator can be determined using least squares techniques in a closed-form manner when fixing the pose and shape. For shape optimization, we use 2D keypoints to refine the bone length of the human body. The loss we use to train beta is between the projected 2D bone length and those computed from given keypoints. Our core module, however, is pose refinement. With camera location and bone length, we can calculate the two possible bone directions from the parent to the child joint. Then we adopt a decision tree along the kinematic tree to trace all the possibilities. Any path traversing the tree is a hypothesis, and we select the most likely path based on the initial HMR estimate since the original prediction is sufficiently accurate at indicating whether the bone points towards or away from the camera. Our ablation studies confirm the effectiveness of each module, with pose refinement being the most critical, followed by shape and camera refinements. Here, KITRO steadily decreases error over iterations and can converge. This table shows that KITRO is compatible with various HMR base models. In addition, KITRO can get extra improvement on top of other refinement methods. We also studied how much examples get improved. Looking at this histogram here, most majority of samples, over 88%, improve. Here we compare our approach with the SOTA human mesh refinement methods. By comparing with optimization-based methods, like CLIF and Simplify, our KITRO demonstrates a significant enhancement over them. According to the visualization, KITRO refines the pose progressively and delivers more accurate alignment with 2D evidence, avoiding common issues like depth penetration. Our method has some limitations. KITRO relies on accurate initial HMR and 2D keypoints. Inaccuracies in these can undermine its effectiveness. Future work will address 2D keypoint noise, incorporate video information to refine all factors collectively, and transition from camera to world coordinates. To conclude, KITRO's explicit depth modeling and closed-form calculation diminish ambiguities in solution space, enhancing depth accuracy and obtaining ideal 2D fit simultaneously. KITRO's decision tree-based hypotheses tracing and selection for joint rotations encompasses the entire kinematic tree, benefiting both end joints and the joints near the root. The takeaway is that for ambiguous problems like 3D refinement by the help of 2D, we can try to decompose the entangled factors. By doing so, we are often led to elegant, closed-form solutions which can be a preferable alternative to gradient-based optimization.